In this section we are going to discuss the basic principle of neural networks. And in particular we will discuss the central union of neural networks, the artificial neuron, which is essentially just an affine function of its inputs. So this can be inputs from your features or from other neurons. And this affine function of its inputs is called the activation. And then this is followed by a nonlinearity, so a nonlinear function. And this function is called the activation function. And the basic principle of neural networks is that they are a computational graph, a network of neurons. So each of these single neurons is a simple nonlinear function, and by combining them we can come up with high-dimensional complicated function, which can be used to solve our engineering problems. And we'll discuss why we actually need this nonlinearity. So there's a mathematical reason. If we would leave away this nonlinearity, then all these neurons would be affine functions. And we'll see that this doesn't work, that we will actually be stuck with affine functions. And however, if we include these nonlinearities, then even very simple structures of neural networks will yield universal approximators, which essentially means that we can approximate any function we like with a neural network. So let's get started with the neuron, or the unit, which is the basic building block of our neural networks. And essentially this is just an affine function of inputs. So we have inputs xi, and we have uppercase D of them. So this sum here runs from I to D. And each of the inputs gets just weighted with a private weight wi. So we just weight each of the input with a private weight, and we sum this up. And then we add a bias term. And this essentially is an affine function. So only this here, the sum over the weighted sum over inputs is a linear function. If we add a bias term, this is an affine function. So this is an affine function of the inputs. And so this affine function is called A. So this affine function is called A for activation. And so after having computed this affine function, then this just goes in a nonlinear function phi. So this is a function mapping real numbers to real numbers, and this is a nonlinear function, and often called the activation function. So this is the basic building block, just an affine function of inputs followed by a nonlinear function. And this is this here. And well, the output is called here y hat. And so this is the central unit, the union, just an affine function of x followed by nonlinearity phi. And we'll introduce now a certain notation. So as just said, we have an affine function followed by a nonlinear function phi. And we will now make this bias term here implicit. So this bias term is important in neural networks, but often is clutters notation, and we will absorb this bias term into these weights here. And we do so by including a dummy feature. So our features run from I to D, and we'll introduce a dummy feature x0, so a zeroth feature, which is just constantly 1. And we'll introduce a corresponding weight w0, which takes over the role for the bias. So by just defining this w0 as b and having this constant input 1, so 1 times this w is always this w0 is always this w0, and essentially this takes over for this bias term here. So we can absorb this bias now into the weights, and now essentially we change the running index here from 1, starting from 1 to 0. And by including this dummy index and this additional weight, we can make the bias term implicit. So the bias is important, but the clutters notation, we can absorb it with this trick into the other weights. So we can write this neuron also as a computational graph. So here, this is again the neuron, this affine function, followed by nonlinearity. And we can draw this as a computational graph. So here we have all our features. So here this is the dummy feature. And essentially we can figure that all these inputs essentially travel over these edges, and on these edges there sits these weights, and while our numbers here travel over these edges, they get weighted with these weights. And here they get accumulated, so this is the sum of the affine function, and then the result of this accumulated input, so the activation A, goes through this function phi, so this maps A to the output y hat. And so this is the computational graph, and really just the same as we had here or here. And often we don't draw it as explicitly, so often we don't draw this accumulation or this sum explicitly, but we combine the sum with the nonlinear function just in a single node. So you can actually, this is the same picture, but you can figure that this activation is just computed before this nonlinear function. So often we don't draw this like as explicit as here, but this is often kept implicit here. So this is the neuron as a computational graph. And now the basic principle of the neural network is just make this graph bigger. So combine many of these neurons to a network, so like this here. So again, here we have some inputs, and so these inputs travel in one neuron phi1, for example, and in another neuron phi2, and then the outputs of these neurons, they go into another neuron phi3, and phi3 goes in another neuron phi4, and also phi2 gives input here, and then this is the output. So essentially this computes a function, so from our d-dimensional input, so the dummy term doesn't count here, so d dimensions to one output, for example. But we could also have like several units here as output, and then we would have a d-dimensional function mapping to several outputs. And so the motivation, like in biological neural networks, artificial neural networks are just networks of neurons. And so each of these neurons is actually simple. It's an affine function followed by some nonlinearity, and we will discuss in a bit which kind of nonlinearities we are going to use. So each of these neurons is actually a simple function of its input, but if they get combined into a network like shown here, then we can make more complicated functions, so mapping these d dimensions to maybe one output or even several outputs. And so essentially, more or less any engineering problem, so any data mining problem, any machine learning problem, can usually be formulated as function approximation. So for example, for classification, if you want to classify apples and pears, so images from apples to pears, then it is essentially just a function from a pixel vector to a binary decision. So this is a complicated function, but it's just a function. Same holds true for regression, and many other advanced applications can be formulated as function approximations. So this is actually the idea of artificial neural networks. Flexible function approximations by combining many simple functions. And the main idea is that we can train now these neural networks by optimizing the weights. So here we haven't shown the weights in order to clutter the graph less, but essentially you can figure that on each of these edges essentially there sits a tiny weight, which essentially just multiplies the corresponding number which travels on these edges. So the idea is we have neurons, and by combining them into a computational graph or a network of neurons, we get actually complicated functions. So why do we actually need this nonlinear activation function? So we said each of these neurons is an affine function followed by a nonlinear function phi. So why is this really necessary? So actually two reasons. So figure that we had only one neuron, then this would just be a linear function or an affine function. And so linear functions are often not adequate for real-world data sets. So see also support vector machines. We saw that just by applying the kernel trick, we could boost support vector machines quite significantly, so boost their performance, which essentially made support vector machines a nonlinear classifier. But more importantly, so artificial neural networks have this plug-and-play philosophy. So combine many neurons to a more complicated function. And this principle does not work with linear neurons, so with affine functions. And I'll show you why. So here is an example where we have omitted this nonlinear function. So this is now just a neural network consisting out of affine functions, so linear units essentially. And here, so here we have again the inputs, and here we have now one linear unit, so without this nonlinear function phi, so just accumulating the weighted inputs. And here is another linear unit, also just accumulating the linear inputs, and they go on further to this neuron here, and this is the output. So essentially this is a neural network consisting out of 3 linear units, so 3 affine functions. And I've arranged these units in layers. So essentially here is a first layer. So this is a dummy input to this second, to this last neuron. So here in this layer we have this dummy input. and these two units, and we have essentially a second layer, which is this output here. And here I introduced some naming convention, namely these. So neural networks can become easily complicated, and so we have a naming convention for the weights. So we have this superscript, which essentially indexes the layer. So all the weights here have the superscript 1, which indicates that they belong to this first layer, and all the weights here have a superscript of 2 to indicate that they belong to the second layer. And we also have subscripts. So here we have 01, which means it comes from the 0th input, this dummy input, and goes to the first unit here. Or like here we have subscript 21, which means it comes from the second input and goes to the first unit. Or here D2, which means it comes from the dth input and goes to the second. So again, superscript indexes the layer, and subscript indexes, so the first index is from where we come and the second where we go. So in order to make some sense here. So we have now this nice neural network consisting of 3 affine functions, so linear units. And this is actually just the same as this graph, just written as an equation. So here we have this weight here coming from the dummy input, and then we have a sum over these two neurons, and essentially these are the first neurons, and essentially this is the second layer neuron. And if you now just multiply this out, so if you just expand this whole equation here, it turns out that when you expand this and rearrange for x, that this just collapses back to an affine function over x. So actually this neural network collapses back to a single linear unit here. And so essentially how this works is expand this line and rearrange the weights as follows. So define W0 tilde as this polynomial. So this is a polynomial of the original weights here. And essentially you can see this by just expanding this equation and rearranging according to the axis. And if you define this W tilde like this, you will find that this neural network is actually just equivalent to a linear unit. So, and this holds no matter how big you make your neural network. If you use affine functions only without nonlinearity, it always will collapse back to a simple linear unit. So you cannot get out of affine functions if you just combine affine functions to a neural network. So in a nutshell, a neural network of linear units is just a linear unit, or equivalent to a linear unit. Now, does now nonlinearity save us? So if we now reintroduce our phi functions, can we now express complicated functions, expressive functions? And so to this end, let me introduce the first real neural network, a single layer neural network. And this consists of the input layer. So this is just our input features, again with the dummy input. And now we introduce a so-called hidden layer with uppercase H hidden units, and each of these units is just one of our standard neurons. So before we had, in the linear neural network, we tried what happens if we combine neurons just consisting of this sum here, and now we again apply these phis here. So in this whole layer here, consisting of uppercase H units, so 1, 2, 3, and so on out until H, all of them have the same form. So they have different weights, but they use the same nonlinearity phi. And essentially this can be interpreted that these hidden units, so these units here on this hidden layer, they essentially compute some unobserved features. So like if these are our input features, if we take now affine functions and subject them to a function phi, then this can be interpreted as a feature, so that we extract features from our input vector here. And so these features are not observed, so our observed data is the x and the label. But these features are like kind of hidden features, and therefore they're called hidden units. So the nonlinearity is just a function mapping from the real numbers to real numbers, and this is fixed here. So each of these units have the same nonlinearity. And here the output layer, so this function of x, so y hat, we call the output y hat usually, is now just a single linear unit. So in general, the output layer can have multiple units, but here we show it only with a single unit. So very simple structure, just your inputs. They get a layer of units, and the units are all identical except the weights. So the weights are independently tuned, but the nonlinearity is the same. And this is a single layer neural network. Now a simple structure, but it turns out that this structure is already sufficient to approximate essentially anything. And this is formalized with the universal approximation theorem, so which says, so any continuous function, so it must be a continuous function, but this is often enough for engineering disciplines. So any continuous functions which maps from the d-dimensional space to the o-dimensional space, and again here O was just 1 because we had only one output, but essentially we can, if we have in general O outputs, if we have such a structure, a single layer neural network, so any continuous function Rd to Ro can be arbitrarily well approximated on any compact set. So it needs to be a restricted set, so it cannot go from -infinity to infinity, for example, but it must be bounded. So any such function can be approximated by a single layer neural network, this one, for a wide range of nonlinearities phi. So we can keep the nonlinearity phi fixed for every of these guys. The crucial thing is that this phi must be non-polynomial. So it must be non-constant, non-linear, non-quadratic, and so on. Essentially, as long as you are satisfied that these are non-polynomials, you can approximate any continuous function with this structure. So this is a very strong result, which means neural networks can in principle approximate any function arbitrarily well. The function which maps apple and pear images to the class decision, which is a high-dimensional complicated function, can be approximated with a neural network. So we haven't yet talked about these nonlinearities, phi, so nonlinear functions, and we saw it's important that they are non-polynomial. So what can we use? So there are these more traditional nonlinear activation functions. So in the 80s and 90s, people really like to construct neural networks with a sigmoid, so S-shaped functions like this sigmoid function or the hyperbolic tangent. So here we see the definition of these functions. And more recently in deep learning, people like to use more functions like the rectified linear unit or the leaky rectified linear unit or the exponential leaky unit. The advantage of these units is actually, so some of these units are very cheap to compute. So for example, the rectified linear unit is actually just the max of 0 and x. So essentially the rectified unit is just 0 for negative inputs and just the identity for positive units. So this is very cheap to compute. And also what is common with these more modern activation functions is that they are unbounded. So these traditional activation functions, they saturate quite quickly, so they become flat. And this means that the derivative of these traditional functions is 0 over a wide range. And the activation functions here, the derivative actually becomes non-zero over a wide range. And so traditional activation functions had this problem of the so-called gradient diffusion problem, so that the gradient of the so for learning we will see later that we will derive the gradient of our weights, and if you use like functions like these which are flat over a wide range, then your gradient will become very quickly 0 and you cannot learn anything. And these modern functions which are unbounded, they fix this problem essentially. So all of these functions are non-polynomials and therefore actually satisfy this theorem. And in principle, any of these functions can be plugged into your single layer neural network, and you will have in principle universal approximation. Of course, it doesn't tell this theorem doesn't tell you how many hidden units you actually need. So potentially you need a lot. So these are common activation functions phi. And for learning, I already indicated that we need the gradient or the derivative. And we will also need the derivative of our activation functions. And activation functions, so like these ones, are typically chosen that we also can compute the derivative easily. So for example, here we have again the sigmoid. This is this function. Here, this is the sigmoid function, and the derivative can be easily shown to be given by this formula. So the derivative, the sigmoid, actually turns out to be the sigmoid again times the sigmoid, but with flipped argument. And for the ReLU, which is this max of 0 and x, so this kink here, it's easy to see that the derivative, so for negative arguments, it's just 0. For positive arguments, we have just the identity function, so here the derivative is 1. So this is just the indicator whether x is larger than 0. So to illustrate this, here we have the sigmoid function, so this blue function is the sigmoid, and here this red function is just given, so this is the derivative of the sigmoid, and this is just given in closed form. And again, we'll typically pick disactivation functions so that they are non-polynomial, and that we also can compute this derivative easily, because we'll need this in learning later. And here is the ReLU, so the blue function here is the ReLU, just this kink function, and here the derivative is essentially just like this step function. So here in the positive, for positive values, it's just constantly 1. So this already concludes this section. So we discussed the neurons, which are affine functions of the inputs, followed by nonlinearity, phi. And a neural network is actually just a computational graph or a network of these neurons. And the idea is to construct complicated high-dimensional functions out of these simple units. And we saw that nonlinearity is key. So if you build a neural network with only linear units, without nonlinearity, we'll just get equivalently a linear unit out of this. And we saw that already a simple structure, so a neural network with a single hidden layer, so identical nonlinearity, as long as the nonlinearity is non-polynomial, yields a universal approximator of continuous functions. So this means you can approximate any function you like with a neural network.